let's continue with quiz review 5.2, 5.4, 5.5, and let's continue with number 7. So indefinite integral of dx over quantity 2x plus 3 squared. And we can't expand this, so we look to the denominator to find our u value. We look inside the parentheses, so we're going to let that be our first guess. Our u value, 2x plus 3. We find the derivative with respect to x. 2x turns into 2, 3 goes to 0. Solve for dx, we get du over 2. We make our initial substitution. What's inside the parentheses gets replaced with u, so we have 1 over u squared. Dx gets replaced with du over 2. So I can pull the 1/2 out, so now I have 1/2 times the indefinite integral of 1 over u squared du. Now, we can't apply the natural log rule here because natural log rule only applies for integrand that is in the form of 1 over u to the first power. In this case, we have 1 over u to the second power, so any degree other than 1 in the denominator, we're going to have to use power rule. So, but if we think about power rule only works if our variable is sitting up in the numerator. So we have to put this u value up top. So we have to change this to u to the -2. Now we can apply the integral rule using power rule. So u to the -2 becomes, we add 1 to the exponent, so u to the -1 over -1. We still hold on to that coefficient 1/2, and we plus c. Okay. I'm going to clean this up, continue to clean this up. This u to the -1 drops down to the denominator, and I get -1 over 2u plus c. And finally, let's replace our u value back in terms of x. So -1 over 2, parentheses, 2x plus 3, and then finally plus c. All right, number 8. If we look at this problem here, we can't really split this up into individual terms. And if we think ahead, our u value of x squared minus 4x plus 8, our derivative will not be enough to match with this denominator. And if we let the u value be x minus 3, we know that will definitely not cancel out with the numerator. So we have this method of using division to help us rewrite this fraction in terms of a quotient. So we're going to use synthetic division here just because the denominator is in the form where it is a variable to the first power and a constant. So the way we can do that is we can, rather than go through long division, we can go through synthetic division. And what we do is we take the opposite of the constant and we put it outside a half box. And then inside the half box, we're going to put the coefficients in order of decreasing exponent. So we have 1, -4, and 8, because this goes from x squared to x to the first and down to a constant. If we have any missing degrees, let's say if it was x cubed and then 4x and plus 8, then we're going to have a placeholder for a variable that is not represented. So, but in this case, we have x squared, x to the first power, x to 0, or the constant. So all these are represented. So we have 1, -4, and 8. So now we go through and find the quotient. So we always bring the first term down, which is in this case 1. Now we take the 1, multiply it with this 3 on the outside. So 3 times 1 is 3. We combine it with the value above it. So -4 plus 3 is -1. Multiply it again with our value here. So 3 times -1 is -3. 8 minus 3 is 5. So now we have coefficients that represent our quotient after we've gone through division. But we're going to have to make sure that each of these, the variable that is attached, is going to go down by 1 degree from our initial problem. So x squared will go down to x to the first power, and everything will decrease by 1 degree. So this place was initially x to the first power, but now it's going to be a constant. And then the last term is going to be the remainder. So the remainder is 5, and we can't divide any further with the divisor, so we say 5 over x minus 3. Now all we've done so far is we have just rewritten the problem in a different form. We haven't done anything to solve yet, but this form, as you can see, is a lot more, it's a lot easier for us to apply the rules that's available to us. So these two terms, we can use power rule, and this term, we can use the natural log rule. Okay, think of this as going through U-substitution, and 5 over U is simply 5 natural log of absolute value of U plus C. All right. Power rule, x becomes x squared over 2. Negative 1 is a constant, will turn into negative x. So we just treat each problem with its own appropriate integral rule. Right. Number 10. So skip the number here. We go through the same process. Denominator is in terms of x minus k. So we can go through synthetic division. Again, we can't split up into individual terms. We can't rely on U-substitution yet. So we're going to rewrite this in a different form, and hopefully that will split some things up for us and allow us to apply the appropriate rules for integral. So we take the opposite value of whatever constant you see here outside. So 1 turns to negative 1. And we go down the line and we write the coefficients of each value in front. So we have 1, negative 5, 1, and negative 2. Okay, we bring the 1 down, multiply with the value outside. So negative 1 times 1 is negative 1. Combine with the value above it by adding. So negative 5 and negative 1 is negative 6. Multiply with the outside number, so we get 6 plus 1 is 7. 7 times negative 1 is negative 7. Combine with the value above, so negative 7 minus 2 is negative 9. Now each coefficient will decrease by one. Each variable will decrease by 1 degree. So x cubed will turn into x squared. So this is what we have: 1x squared minus 6x plus 7. And finally, our last value is the remainder. So we put that value over the divisor. Again, we haven't done anything to solve the problem yet. All we've done is we've rewritten the problem in this different form. Okay, so now we go through power rule. Each of these terms are separated by different terms. By plus or minus, so we can apply the appropriate rule. So power rule for the first 3 terms. So x cubed over 3, 6x squared over 2, 7x, and finally the last is applying natural log rule. So 9 natural log of absolute value of x plus 1 plus c, and we finally clean this up here. Okay, last few problems here. We have the integral of e to the 3 minus x dx. So if we think about this, looks like the form of integral of e to the u, so that's exactly what we're going to be trying to apply, which means that our u value will be this exponent 3 minus x. So go through our derivative. Negative x turns into negative 1. Dx equals negative du. We make our substitution. The integral of e to the u times negative du, so we have to pull a negative outside, and the integral is simply going to be the same as the original function, so negative e to the u. Now we're going through U-substitution, and this is definite integral, so we have to convert our initial bounds, which are in terms of x, to be in terms of u so that we can evaluate. So we have to use what's assigned that relates u and x, so we can plug in. So lower bound was initially 3, so plug 3 in for x. 3 minus 3 is 0. Our new lower bound is 3. Plug 4 into our assignment. 3 minus 4 is negative 1, so our new upper bound is negative 1. So plug negative 1 into the antiderivative first, so negative e to the negative 1, minus, now we can plug the lower bound in, so 0 plugs in for u, so minus e to the 0. Now e to anything raised to the 0 power is going to be 1. The two negatives cancel out, so we get plus 1. I'm going to resolve this negative exponent, bring it down to the denominator, so negative 1 over e plus 1 is the solution to our definite integral. All right, number 12. This is also in the form of e to the u, but now our u value is more complex. But if we think about what's going to, Okay, if we think about what's going to happen to this x squared, our derivative will turn into a 2x, which will cancel out with this x. Okay, and then we can kind of look ahead and see that we do have the necessary parts to be able to cancel out, to be left with a rule that we can apply. So we let the u value be the exponent, -1/2 x squared. Find the derivative, -1/2 times 2x. Simplifies to be just -x. Solve for dx. We get dx equals du over -x. We make our substitutions. This x stays initially, e to the u. And dx gets replaced with du over -x. The x's cancel out. We pull the negative in front. So we have the negative integral of e to the u. Okay, we know e to the u will just be the same as the antiderivative will just be the same as the integrand. So negative integral of e to the u will turn into the same, negative e to the u. Again, we have to go through U-substitution because we have to convert our bounds to be in terms of u because we're going through U-substitution. So our old lower bound, plug in for x, that relates into the equation that relates the two variables. Plug 0 in for x, and we get u is equal to 0. So lower bound is not going to change. Plug root 2 in for x, and we're going to get -1/2 times root 2 squared, which allows the 2's cancel out, leaving us with a new upper bound of -1. So we plug the upper bound in first, negative e to the -1, minus, plug in the lower bound, 0 in for u, e to the 0. So this cancels out to actually look exactly the same as number 11. So that's just a coincidence there with the same solution. All right, number 13, we have to look at our other potential rule that we can use to solve this. So this is actually in the form of a to the u. So this is similar to the e to the u, but now we have a base that is not e. This is a base a. So we see the base 5 raised to the secant x. So if we let the u value be secant x, and if we think ahead, that derivative will cancel out with the remaining trig functions that we see there. So we let the u value be secant of x. Derivative is secant tangent. Dx is du over secant tangent. We make our substitution. 5 to the u times secant tangent x. And then dx gets replaced with du over secant x, secant tangent. The secant tangent cancels out, so we're left with in-depth integral of 5 to the u du. And if we think about the rule that we just learned from 5.5, we do have a rule for a to the u, which is a to the u divided by natural log of a plus c. So that's exactly what we do by applying the rule that's available to us and replace our u value back in terms of x, in this case secant of x. Right. Last problem here. This is just simply seeing if we can recall all the trig rules. So we can just split this up into, this already split up into individual terms separated by plus or minus, and all these are going to be log rules. So tangent of x is simply negative natural log cosine of x. Secant is simply natural log of secant plus tangent of x. So I left out a plus here. Cotangent is simply natural log of the absolute value of sine of x, and cosecant is negative natural log of cosecant of x plus cotangent of x. So again, we have, this should say secant of x plus tangent of x.